In this video, we will be describing how to calculate the Gibbs free energy for a reaction that is not under standard state conditions, as well as how to determine the equilibrium constant from a Gibbs free energy value. So as a reminder, the superscript not means that you are working under standard state conditions. So if you have this superscript 0 or not for a delta G, a delta H, or a delta S, that means that you are working under standard state conditions. If you do not have that superscript not, as is the case here, you're working under non-standard state conditions. As a reminder, standard state conditions are when you are working in the normal state for your compound at that particular temperature. So for example, carbon dioxide at room temperature, 25 degrees Celsius, is a gas. A non-standard state would be if we had it as a liquid or a solid, or water, H2O, in the form of a liquid at 25 degrees Celsius is its standard state. Water vapor and ice, or water as a solid, are non-standard state conditions because those are not the normal state at that particular temperature. The partial pressure for all gases under standard state conditions are 1 bar. The standard concentration for standard state is 1 mole per liter. So any aqueous solutions will be at 1 mole per liter. If you're working with a reaction system in which the concentrations are not 1 mole per liter, then you are not working under standard state conditions. This would actually be the case for the majority of situations. It is only rarely that you are working with concentrations that are all at 1 mole per liter. And as soon as the reaction starts, you no longer have 1 mole per liter of all your components because they are changing. Reactants are going to products, or products are going to reactants, depending on how your system was set up. So under non-standard state conditions, we need to take into account the driving force that we get from having our concentrations that are away from this 1 mole per liter. The way that we do that is we use our reaction quotient, the same thing that we had when we were talking about equilibrium. So the relationship between the Gibbs free energy under non-standard state conditions and the Gibbs free energy under standard state conditions, they are related by this plus RT ln Q. Now, because the Gibbs free energy is an energy, it has units of joules or kilojoules per mole. So the R value that you're going to be using needs to be in joules. So you will be using the 8.314 joules per mole Kelvin. The T is temperature, needs to be in Kelvin so that your units will work out. The Q is the exact same Q that we were working with equilibrium. So that Q is products over reactants raised to their respective coefficients, leaving out solids and pure liquids. So if we're at equilibrium, that would be where there is no driving force for the reaction. Again, a reminder, the Gibbs free energy is sometimes called the chemical potential. It represents the maximum amount of work energy that we can get out of a system under constant pressure conditions. So if we're at equilibrium, the reaction has no driving force to go anywhere. If the system is at equilibrium, neither the forward nor the reverse direction are favored. The reaction maintains their concentrations, and so there is no driving force, which means that if we are at equilibrium, the chemical potential, or the chemical driving force, which is the Gibbs free energy, is equal to 0. Under these conditions, if we look at our equation here, relating our non-standard state condition Gibbs free energy to our standard state condition Gibbs free energy, if we're working at equilibrium, then Q becomes K, and delta G, without the not, just the delta G for the non-standard state Gibbs free energy, becomes 0. So we end up with 0 is equal to delta G naught plus RT ln K. Rearranging that equation gives us that delta G naught is equal to minus RT ln K. What this does for us is we could either figure out the Gibbs free energy if we know the equilibrium constant, or figure out the equilibrium constant if we can figure out the standard state Gibbs free energy. Previously, when we had talked about equilibrium, we had mentioned that there is a driving force pushing the reaction towards equilibrium. And we could get an idea of the directionality of that driving force by comparing our reaction quotient Q with our equilibrium constant K. If we had a situation where Q was less than K, then there would be a driving force for the reaction to go in the forward direction to make more products as it goes towards equilibrium. Conversely, if Q is bigger than K, then we have too many products and the reaction will go to try to remove some of those products by pushing towards the reverse direction, making more reactants as it goes towards equilibrium. The further away from equilibrium we are, the greater the driving force is for the reaction to proceed in the particular direction that it will go. That driving force is the Gibbs free energy. So the larger the Gibbs free energy, the greater the driving force. And the further we are from equilibrium, the greater the Gibbs free energy is going to be. If we're thinking about using something as a fuel or an energy storage device, pushing the reaction further from the equilibrium value allows us to store more energy to be used later. So if we're talking about like a battery, for example, having more of the components in the charged or reactant form enables us to store more energy, which we can then get out to get more work done. So because our Gibbs free energy of reaction without the superscript naught is equal to 0 at equilibrium, as we had said, the delta G naught is equal to minus RT ln K. We can now look at our K values and our delta G values and look to see whether that tells us something about the spontaneity of a particular direction of the reaction. So if we're looking at our equilibrium constant and our equilibrium constant is less than 1, we are taking the natural log of a number less than 1, which would be a negative value. So this would be, our delta G would be equal to the negative of a negative number. R is a constant, which is positive. T is temperature in Kelvin, which is also always positive. And so we'd have negative times a positive times a positive times a negative value. This would result in us having a positive delta G, which would tell us that under standard state conditions, the reaction would be spontaneous in the reverse direction. So if we have everything under standard state condition, the reaction will push back towards the reactants. When our K value is greater than 1, the delta G naught is going to be negative. So if K is greater than 1, plugging into our equation up here, we take the natural log of a value greater than 1, which would be a positive number. So we got negative times a positive times a positive times a positive would give us a negative value. Delta G is therefore negative, or delta G naught is therefore negative, and the reaction will be spontaneous in the forward direction under standard state conditions. If K is equal to 1, which won't happen all that often, but for some processes it could be 1. If K is equal to 1, then our delta G naught is going to be equal to 0, and the reaction is at equilibrium under standard state conditions. Now, in our previous discussion on equilibrium, we had mentioned that the equilibrium constant does change with temperature, but at that time we had been just using Le Chatelier's principle to predict the direction that it would go. Now that we've incorporated the Gibbs free energy with the equilibrium constant, we can actually determine what the equilibrium constant will be at a new temperature. So we have two equations that we have for our Gibbs free energy. Our Gibbs free energy in equation number 1 here is delta G naught is equal to delta H naught minus T delta S naught. At equilibrium, delta G naught is equal to minus RT ln K. We can actually combine these two together because the top equation, the delta H naught minus T delta S naught, is equal to delta G naught, and then the bottom equation, the minus RT ln K, is also equal to G naught. So because both the top part and the bottom part are equal to delta G naught, they are equal to each other. So we can say that minus RT ln of K is equal to delta H naught minus T delta S naught. If we're interested in figuring out how our equilibrium constant changes with temperature, we can divide both sides by minus RT. On our left-hand side, the minus RTs would end up canceling out. On the right-hand side, the negative here will cancel out with this negative here, so we'd have a plus. The T's are going to cancel out, and the result is we would get this equation here. Now, the 1 over T here has been brought separate from the delta H over R because we can actually plot this expression out as a linear equation. So if we plot on our y-axis the ln k, then our term here, these are all constants, this would be our m, this value here, the 1 over t would be our x, and then this, the delta s naught over r, would be our b. So if we plot our graph of 1 over temperature on the x-axis and the natural log of k, what we would get is, depending on the sign of our delta H, we would get a line. The intercept here would be our delta S naught for the reaction over R, and our slope would be equal to minus delta H for the reaction under standard state conditions divided by R. So this is actually a way that you could experimentally determine the change in enthalpy and change in entropy for a reaction, which would then enable you to back calculate the enthalpy of formation for any new compound that you have made and put it into one of the tables. This would be RxN. Okay, so because this equation has the form y equals mx plus b, once we figure out the general equation, we could find the delta H and the delta S, or if we have the delta H and the delta S, we can then use this to figure out a K value at any new temperature. Another way of figuring this out would be to use the equation ln of K is equal to our delta H over R, 1 over T, plus delta S over R. We could take this whole thing, get rid of the natural log by raising both sides, by raising e to both sides. This would give us K is equal to e raised to the quantity minus delta H over R, 1 over T, plus delta S over R. And if we were working at a particular temperature and we knew the Gibbs free energy for that temperature, we could replace what's in here with our Gibbs free energy. So we could also write this out as K is equal to E to the minus delta G over RT. Right? Because this term on the inside of our bracket here, the thing that we're raising everything e raised to, this is the same as our minus delta G over RT. So these are a couple of different ways that we could find the equilibrium constant at a particular temperature. You would first start by calculating the Gibbs free energy at that new temperature and dividing it by RT. E raised to that number would give you your equilibrium constant.